Hello again. Tonight we're once again going to be talking about radiation reflection pressure. This is part three, and the reason why there is a part three is somebody asked me to do an additional test, and I had to do it. So we'll get into that. So as the saying goes, get ready for another minutia-filled science and technology presentation. This is part three. This is for those that are doubting Thomases who said, "Have you tried it in a vacuum?" It's actually harder to do in atmosphere, but okay, I'll try it in a vacuum. Or as the saying goes, he tasked me, I had to do it. So if you're brand new to this topic, you can read the first few slides. That's part one. If you've already seen the proof in atmosphere and other scenarios, you can jump to part two. If you've seen that, but you want to see it in vacuum, you can jump to part three. This one will be kind of skipping over parts one and two and going straight to part three, so I don't bore everyone. So I tried doing it under all sorts of different scenarios, and turns out you can do it in air. And I didn't need vacuum or didn't think I needed vacuum. But somebody said, well, you haven't ruled out that it's not heating, not infrared heating of the wires or the printed circuit boards, or I didn't think that would be the case because it's not directly correlating to the red, green, and blue amplitudes that I was doing in the LED, but okay, I'll do it in vacuum. So for those that are not familiar with it, radiation reflection pressure out in space, or just radiation pressure as they call it, there are two effects. There's the Yarkovsky effect and the Yorp effect, which the Y also stands for Yarkovsky, but it's different. The Yarkovsky effect is the daily rotation and seasonal movement of smaller bodies like comets and asteroids and moons and such. It gets affected at a small level, but over time, measurably, on the orbit of these things around the sun and their rotation. And the Yorp effect, which affects the spin, lower and higher speed spin of these objects, makes them rounder or flatter. It changes their equatorial bulge based upon solar radiation, increasing the spin rate of the objects. Both of those occur in the vacuum of space, so there's no denial that photons striking the surface of these objects are the source of affecting that. But it's a very small individual force, less than 1 Newton, but collectively over an object that might be 500 feet across or larger, it's enough to change the orbit and the rotation and the equatorial bulge of these small objects. Okay, if that's not proof, then I'll do the test in vacuum. So the first thing I had to say was, well, I use a computer. I use a Raspberry Pi 02W to do my measurements and record data and such. I've got to find a way to get that to operate inside of a vacuum tank at 100% vacuum, nearly 30 pounds per square inch vacuum inside the tank on a battery. There's no wires going through for power and data. So it's got to operate off of Wi-Fi inside of an extruded aluminum metal container that has a clear glass top that's 1 inch thick. It's a fused silica glass. So will this work in this environment? Well, I think the Raspberry Pi should be fine. I know of a lot of people that have sent their Raspberry Pi by helium-filled balloons to the edge of space, so not worried about that. The batteries should be okay because lithium-ion batteries bent all the time anyway. So how to disperse heat, though? So the Raspberry Pi is going to produce heat, and normally you have a little heat sink fin on top of the hotter chips, and it disperses heat so that the computer doesn't fry itself. Well, if you're in a vacuum, a heat sink's not going to work as efficiently, and certainly a fan won't work. So have to think about these things. If it was one of the bigger Raspberry Pis that produced far more heat, it'd be more something to consider, but I've got one of the smaller ones, so not as much. So what I did was I made the computer slower. I went in the software and I changed how fast it ran. So instead of it running at 1.5 gigahertz, I set it to run at 800 megahertz, which makes it produce less waste heat. And since I'm using Wi-Fi, I set the Wi-Fi interface's transmit power to, instead of being 100%, it's more like 20%. because it's just on my local network in my house. So didn't have to waste a lot of transmitter power with waste heat. Extends the battery life, reduces the heat problem. So if you ever want to do something like this, here's how you actually do it. You go in, you modify configuration file, you turn off the speed boost, and then you set the, I didn't set it to 800 megahertz, I set it to 600 megahertz, correction there. And then you reboot it and you verify it. And also, the Raspberry Pi 02W is a quad core, and I don't need 4 processor cores. So I'll just shut down 2 of them. So I changed the maximum number of cores or CPUs that are running from 4 down to 2. That made it run a lot cooler. And since I don't need Bluetooth, turned off the Bluetooth. That's, wireless communication that I didn't need, and how to verify that it's actually turned off. And then how to set the transmit power of the Wi-Fi interface from 31 dBm down to 20 dBm, and how to confirm that. And now, since I don't have like a HDMI video connected to it, how do I get this thing to run what they call headless? No video, no keyboard, no mouse. Everything is run remotely via the Wi-Fi interface. So I had to connect up the Wi-Fi interface, and I didn't have a graphical user interface, desktop or Windows kind of thing, to configure the Wi-Fi. So I had to figure out how to manually configure the Wi-Fi via the command line interface. And I did. So that's how you do that. Battery power. I had to find out how much power the computer needs, which is 5 volts DC at 2.5 amps, or it consumes 12.5 watts. So I knew I didn't need that because I turned off a lot of stuff and made it run slower. But now I need to match connectors. The power input connector on this particular Model Pi is a micro USB jack. And one of these, a battery pack that you might use to charge your cell phone. I just bought one of those that had the right characteristics, right specifications on Amazon, had it delivered, and that was my battery source. I had to verify everything. The most significant thing is some of these things are so smart that if you give them too low a power demand, they won't switch on. Or if they see the power demand like was high and then drops down low, they'll switch off. So I had to make sure I got a model that didn't have those fancy features. If you remember from the earlier video, in order to acoustically and vibrationally isolate my LED photon emitter from my piezoelectric MEMS microphone, I put it on a polyethylene foam block. Great when you're in normal atmosphere. The little air bubbles inside the polyethylene will uncontrollably expand under vacuum. And I didn't want that to change the alignment of the photons hitting the microphone. And I didn't want it to tilt things out of alignment. So I changed what it was mounted on. I got a macaroni box, a paperboard macaroni box, and I cut a little strip of it, and then I bent 2 little peaks in it that were 5.5 millimeters apart, and cut slits in the top, and then I put the printed circuit boards in there. I put tape on the bottom to hold the folds in place, and then I put a block of regular styrofoam underneath it just to isolate it from the metal aluminum bottom of the vacuum tank. So that was my cobbled together suspension inside the vacuum tank. And here's a current version of Best Value Vax vacuum tank kit. It's a 5-gallon vacuum tank. It's made out of extruded aluminum. The top is 1-inch thick fused silica glass. It has a silicone rubber over O-ring seal. You can flip it upside down. So if one side gets too worn from use, you just flip it over and you can buy a replacement seal that just snaps on there. All of the plumbing fittings and the gauges and valves and stuff dress out the side of the tank, not through the glass top. I wanted to be able to take pictures through the glass top. On the left there around the hose, you see the little rectangular mat. That's just an isolation mat, because in the early days of this company, BVV, they sold supplies to make enjoyable chemical things. You could dry and produce residue sap, things that are now allowed by individual consumers in Florida. But back when they first came in, you could buy these in 1-gallon, 3-gallon, and 5-gallon tanks. And when I went to buy my 5-gallon tank, about 5 years ago, why do you need 5 gallons? And I said, I'm not using it to make the normal product I'm using it for science. Okay. So you buy it as a kit. My kit was around $300, but today the same kit's more like almost $500. It's the tank, the lid, the ring, the gauges, the valves, the hose, the mat that goes inside the tank, and over on the right you see a little 6 gallon per minute vacuum pump, and it's a 2-stage vacuum pump. It's electrically powered. That's your vacuum tank solution. The only difference between this one and mine, other than the fact that mine was cheaper from years ago, is you see all the purple? I don't know why they picked the color purple, but mine is in orange. So wherever you see purple, mine is orange. So I did the testing inside the vacuum tank, and I did controls. So the first thing I did in the top right picture there, you see the battery pack, the computer, and the photon emitter and microphone receiver just in open air. That's sitting on top of my induction cook plate in the kitchen. That's my lab. And I did measurements there. And then I put it inside the vacuum tank at normal air pressure. So you can see it on the right there, sitting inside the vacuum tank, but it's not under vacuum. And I didn't start the pump yet, so it's just at normal air pressure. I wanted to make sure it worked inside the metal container under the glass. It did. Then the next thing I said, well, let me try it at 50% vacuum. So you can see the gauge there, it's swung halfway, because I wasn't 100% sure that this brand new battery pack that I bought wouldn't self-destruct under a vacuum. I tried it at 50% vacuum, did all the measurements, and then I said, looks good. And then I took it to 100% vacuum, and you can see the gauge on the lower right there. It's down at the bottom. It's, as far as it knows, all the air has been removed. I'm sure there's some parts of air per million that are left in the tank. It's not a deep space vacuum. It's just a easy to come by vacuum, but it worked. No issues with the electronics, the battery, or the software at either 50 or 100% vacuum. I still got the data, and we'll go to the next slide, which actually shows the data. Okay, doubting Thomas, it's now been done in a vacuum. It actually looks better in a vacuum than it did in air pressure. So it's not the heating from the wiring because I'm in vacuum. There you go. This is the results. So the tests go top to bottom. The first one is the ambient outside the tank, then inside the tank at ambient, then at 50% vacuum, and then at 100% vacuum. You'll see the 4 blobs of color. Now, why the top one is blue and the other ones aren't, it's because I had the cursor, like the audio waveform analysis editor that I was using. I had the cursor just sitting there. And when you do that, it selects the region, and the region was all the data. So I moved the cursor away, and then it went to green. Has nothing to do with the color of the LEDs. So the very top one is in normal air. And you see that horizontal line that's fuzzy that goes for the full length. That's acoustic noise. And it turns out that that's the fan from my laptop computer, which is in a different room, but the 2 rooms are joined by an airspace. And that's a fan in my garage that was on low. So it picked up that noise. That's acoustic noise. And then inside the tank at normal pressure, you can see that little wiggly wave, but you don't see the blur, because inside the tank with the lid on, even not under pressure, it removed the acoustic noise, and now all it had was electronic noise. This is the signal to noise ratio of the microphone circuit, because I've amplified it to see that. I wanted to see what was there. And then you can see at 50% vacuum, you lose that, and it picked up a higher frequency. And then all the way down at the bottom at 100% vacuum, you see a different frequency, but it's still electronic noise. Now, if you go left to right, you can see 1, 2, 3, 4 little blobs. Those are adjustments to the red, green, blue, and red, green, blue, or white channels of the LED. You see 3 different values in each of them. And in the top left, you can actually see what the LED channel values were. So I picked 3 prime numbers, 191 and 53, and then repeated 191. So the 191 shows you a certain amplitude based upon an increase of photon flux striking the piezoelectric microphone sensor. So you see what looks like sound, but there's no sound. It's photons. And then I backed it down to see that there was a difference. And then I pumped it back up to that 191 to see it again. Now the flat gaps between each of the 191, 53, 191 sequences is because I turned off the LEDs. I set all three RGB LED channels to 0. So there was no output. Now, why the fourth one is so much taller is because all three channels are running at the same time. So there's a greater photon flux. Now, why is there a spike at the beginning of each of the sequences? And that's in the particular DotStar RGB LED chip. When you tell it to turn on, it overshoots. It turns on with a higher output voltage than it needs to. So the brightness very briefly spikes and then stabilizes. And if you look at it close, you'll see these little like fingers of waves inside there because the LEDs run on what is known as a charge pulse that runs at 1.2 thousand times a second. So it's literally switching the LEDs on and off at whatever amplitude, whatever brightness you want, thousands of times a second. And that's why it's kind of fuzzy. And in the absence of air down at the bottom, you'll see that that fuzziness kind of blurs because the heat from the LED has nowhere to go. It can't dissipate, so it just stabilizes. Well, there it is. It's in a vacuum. It's correlated to the red, green, and blue channels and to the amplitude of them. Now we have, including in vacuum, evidence that radiation reflection pressure will affect a piezoelectric-based MEMS microphone. That is, photons are striking the piezoelectric material with sufficient force for it to produce an electrical voltage, and that voltage gets recorded as if it's acoustic audio, even in vacuum where there's no acoustics. Radiation reflection pressure can be detected by a piezoelectric microphone in air, so on the surface of the Earth, at 50% vacuum, kind of like it would be at high altitude on Earth, or on the low pressure of Mars, or in deep space. Photons hitting something transfer momentum to it. And if you still have a doubt, I have a couple of quotes for you. Ripley, believe it or not, NDT is Neil deGrasse Tyson. Facts are true whether or not you believe them. And the universe is under no obligation to make sense to you. It's easy enough to do, cheap enough to do. The system under test can be set up. If you have any comments or questions, send them to me. I'd like to know that I've missed something. Otherwise, give it a try. At least for now, until somebody else pokes a hole in it and I have to go do more work. Enough said. And then I added to the links. I had a lot of links before, but now I have even more links.
So why are the LEDs going on and off 1,600 times per second? I thought they were DC.
No, because that would consume too much power. And where I first discovered this was my laser. I have a 2-watt blue laser pointer, and Helen set up this demonstrator that she was going to be able to use a different color laser that would take the light from the laser, go into a photocell that would produce a DC voltage that would correlate to whatever wavelength and amplitude was striking the photocell. And that would be put through a little amplifier to a speaker. And we did that. And I turned the laser on and it started out with, and then it got very, 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 very high pitched and it was hurting our ears. So I stopped the laser and I looked into it. And if LEDs or lasers are just DC, they're just constant on, they will typically get to a temperature threshold TEM00 where the unit will be less effective and it will consume power and waste that power. So what they do is they have a little charge pulse going on faster than the human eye can follow, 1.2 thousand times a second. And what it does is it switches the light or the laser on and off. And in the gaps, when it's off, that's power it's not consuming, which you don't normally see that. But since I'm recording the audio at 44 kilohertz, that guy Nyquist comes into play. If I want to record something that's 1.2 kilohertz off and on, then all I need is 2.4 kilohertz of recording, and I have 44 kilohertz of recording. So you get to see the laser off on, off on, off on, off on, off on, off on, off on. But it's only there when I have the RGB channel value at a value greater than 0, where you actually see what would be the light output, and you see that gapping in the signal.
So maybe I missed something. So are you saying in a standard LED that built into the LED itself is a switch that makes it go on and off?
Yes, it's called a pulse width modulation circuit, or PWM. And the best way for you to see this is go to a place that has outdoor LED lighting and record video of it. And what you will see is light and dark sections of what to your eyes looks like continuously bright LED. And that's because the frame capture rate of your camera, there being, 120 hertz these days, is actually getting out of phase alignment with the PWM refresh rate of the LEDs. So it looks dark because you're predominantly seeing at that angle it's off as opposed to on.
Sometimes you shoot still photos and you wonder why the thing looks like it's not lit.
Yes, it's for that reason.
Yeah.
You need to shoot a lot of them at high speed, and then you cull from that a good one where it's bright.
That's right. Find the best one when it looks like it's lit. Yeah.
So yes, LEDs that look like they're always on aren't always on. They're just blinking off and on faster than your eye can follow, and they do that so they don't overheat and so they save power. Even the smart light bulbs in your house do that, because the smart light bulbs are LEDs. And how do you get a 60-watt equivalent bulb to only consume 6 watts? Because they're not always on.
I used to work on duty cycles with those things, but it's built in now.
Yes. It's just built into the device. And I had to actually look at the manufacturer's spec for the NeoPixel and the DotStar to see what that value was. So when I saw it in the audio waveform analysis, I would know the timing of it. 1.2 kilohertz in a 44 kilohertz sample. Any comments or questions before I stop recording?
Very diligent. Yes.
Oh, no. It's the minutia that gets you.
That's the best part.
Okay. Let's stop recording.